Thank you for introduction. I'm Shin Kobayashi from ICLR. Today I'm talking about the composite asymmetric dark matter model and its testability with the indirect detection experiment. This talk is based on these two papers. Okay. Oh, this is my contents of my talk. First, I talk about the introduction, and next about the composite asymmetric dark matter model, and the last is the indirect detection signals. Okay, let's move on to the introduction. First, the asymmetric dark matter model is introduced to solve the so-called coincidence problem of the universe. In the today's universe, there is the same order of the abundance of dark matter and baryons. However, in the usual WIMP scenario, it is difficult to solve the coincidence problem because the abundance of the baryon is generated from baryogenesis, and the baryogenesis is introduced to compensate the order of 10 to the 9th discrepancy between the thermal freeze out of the symmetric part of the baryons and the observed baryon abundance. On the other hand, the dark matter abundance is produced from the thermal freeze out of the symmetric dark matter and anti-dark matter in WIMP scenario. So the coincidence is kind of the result of some kinds of fine-tuning in WIMP scenario. However, in asymmetric dark matter scenario, we generate the baryon and dark matter from the same origin of the baryogenesis. So this coincidence looks like the natural consequence, and it is easy to explain the coincidence problem in the asymmetric dark matter scenario. This is the spirit of the ADM. Next, we move on to the concrete model of the asymmetric dark matter. To build the simple and efficient asymmetric dark matter model, the choice of the composite dark matter is simple and realizable. Because we need the strong annihilation cross-section to annihilate away the symmetric part of the dark matter and anti-dark matter in the early universe. So we need the choice of the strong interaction is simple, and we have to put the dark matter mass about the range of 1 GeV to 10 GeV to explain the coincidence problem. So again, the QCD scale in the dark sector can easily tune the mass of the dark matter. So we adopt the SU3D symmetry in the dark sector. And also we add the massive UND symmetry in the dark sector. The reason why we added the massive dark photon in the dark sector is to make the model cosmologically safe, because of the QCD prime. I mean the dark QCD dynamics. There is the extra component in the dark sector, such as pions. The extra component in the dark sector can lead to the overclosure of the universe at the early times. So we have to somehow annihilate or decay this extra component into the standard model. By adding the dark photon, the dark pions annihilate or decays into the dark photons, and next and finally, dark photon can decay into the pair of the standard model, electron and positron pair, through the kinetic mixing with the standard model photon. And This makes the model cosmologically safe and consistent with the standard cosmology. This is why we added the dark photon. And next, we need also a B-Poulter interaction and B-asymmetry generation mechanism, because we have to generate the asymmetric part of the dark matter. And we adapt the leptogenesis to generate the B-symmetry. And also we the interaction between standard model and the right-handed neutrino like this, and the interaction between dark sector and right-handed neutrino can be written as like this dimension 6 operator. And in this operator, Q1, Q2, Q2 corresponds to the dark neutrons. At the temperature lower than the right-handed neutrino mass, we can integrate out the right-handed neutrino, and leads to the B-Poulter interaction between dark sectors and standard model sector. This is the overview of our composite asymmetric dark matter model. And then let's move on to the indirect detection signals. In the usual asymmetric dark matter scenario, there is little chance to detect the indirect detection signals at the present universe, because at the early universe, the symmetric part of the dark matter and the anti-dark matter annihilated away. So there is almost no anti-dark matter at the present universe. So they cannot annihilate at the present universe. However, if there is a tiny Majorana mass in the dark matter mass, the remnant dark matter can oscillate into the dark matter and anti-dark matter. This causes the late time annihilation at the universe. So we can, in this case, we can there is a chance to detect the annihilation signal with the indirect detections. And in our model, and like our model and the simple model like ours, Majorana mass in the dark sector cannot be avoided, because we adapt the B- breaking Majorana mass in the right-handed neutrino sector, and we added the interaction between right-handed neutrino and dark sectors. These 2 points leads to the Majorana mass in the dark neutrons like this. And in the UV theory, this dimension 6 operator can lead to the Majorana mass, like in this mechanism. So with this Majorana mass, we can calculate the late time annihilation signal. The main target of our analysis is the annihilation of the dark nucleons and the anti-dark neutrons. These annihilate into the dark pions, and the neutral dark pion can decay into the a pair of dark photon, and dark photon finally decay into the standard model electron and the positron pairs. We calculated the electron-positron pair fluxes, and also the final state radiation flux from the final decay channel. And we put the constraint from Fermi-Lat observation and the Voyager 1 observation. This is the example of flux and the constraints. And the green dots corresponds to the constraints from the Fermi-Lat observation of Draco. And the blue solid line is the flux of gamma ray from final state radiation. And we set the proton interaction scale as 2 times 10 to the 9th GeV, and the orange line corresponds to the proton scale of the 10 to the 9th GeV. In the region above the green dots is excluded by the Fermi-Lat experiments. And finally, we map these constraints on the plane of dark matter mass and the oscillation timescale. The oscillation timescale is calculated from the Majorana mass, the inverse of the Majorana mass, like this. And the yellow region corresponds to the Voyager 1 experiment, and the green region corresponds to the Fermi-Lat bound. And the red dotted line is the future sensitivity from the gamma ray experiment, such as E astrogram. This is the total constraint on the plane of right-handed neutrino mass and the proton interaction scale. The red dotted line corresponds to the E astrogram, and as you can see from this slide, the Fermi-Lat lacks the sensitivity at the lower scale than 2 or 3 GeV. So at the dark matter mass lower than that scale, there is no constraint from Fermi-Lat. And the gray shaded region corresponds to the excluded by the beam-and-cell asymmetry washout mechanism. And the region above the black solid lines also corresponds to the beam-and-cell asymmetry washout. However, this region is highly model dependent, and some model can avoid this constraint. And we can see that in the case of light dark matter, there is a small but probe and testable region in the future experiment, like in this region. So this is the summary of my talk. We constructed a cosmologically safe composite ADM model. And this model inevitably obtains a tiny Majorana mass due to the interaction with the right-handed neutrino. And we showed that we can probe the energy scale of the proton interaction between dark sector and the right-handed neutrino with gamma ray observations such as E astrogram. Thank you for listening.